Last class you learned dynamic programming and 8-1-12. The beautiful idea of solving each subproblem once and remembering the answer. You saw it turn an exponential Fibonacci into a linear one. But Fibonacci is a warm-up. Today we meet the two problems that dynamic programming is most famous for, the ones that appear in every algorithms course and every coding interview. The knapsack problem and the longest common subsequence, usually shortened to LCS. On the surface, these two look completely different. One is about packing items into a bag to maximize value. The other is about finding the longest shared pattern between two sequences of symbols. And yet, Na2N1 and this is the real lesson of today, Na2N1 underneath, they are solved by exactly the same move. Both come down to defining a table, writing a recurrence for one cell in terms of its neighbors, and filling that table in one cell at a time, until the answer appears in the final cell. Once you see that both of these classic problems are really the same grid filling technique, you have a template that unlocks a huge family of problems. Today, we will set up the knapsack and find its take or leave choice, set up LCS and find its match or skip choice, and then step back to see the single shared pattern beneath them both. Let us fill some tables. Here is our path for today. First, the two classic problems. Second, the knapsack setup. Third, its take or leave choice. Fourth, the LCS problem. Fifth, its match or skip choice. And sixth, the shared pattern beneath both. Let us dive in. Let us begin by meeting our two problems side by side, so you can appreciate how different they look before we reveal how similar they are. The first is the knapsack problem. Imagine you have a bag, an 81-200 that can carry only so much weight, and a collection of items, each with a weight and a value. You want to choose which items to put in the bag so as to maximize the total value you carry without exceeding the weight limit. It is an optimization problem. Out of all the possible subsets of items that fit, find the most valuable one. This models countless real situations, an A212 wall, choosing what to invest in under a budget, what to load under a capacity limit, what to pack under any constraint. The second is the longest common subsequence. Here, you are given two sequences, an A200-200-200, say, two strings of letters, and A200-200-200, and you want to find the longest sequence of elements that appears in both, in the same relative order, though not necessarily next to each other. It measures how much two sequences have in common as an ordered pattern. This too appears everywhere in A21-12, comparing two versions of a file to see what is shared, comparing DNA strands, measuring similarity between sequences of any kind. Notice how different these feel. One is about weights and values and packing, the other about symbols and order and matching. And yet here is the promise of today. These two very different looking problems are solved by the same underlying dynamic programming method. Both have the two properties DP needs and ATC-AT supau. They break into overlapping subproblems, and their best answer is built from the best answers of smaller versions. And both, as we will see, are naturally expressed as filling in a two-dimensional table. By the end, you will see that if you can solve one of these, you can solve the other, because they are the same shape of solution wearing different clothes. That is the deeper skill, not memorizing two problems, but recognizing one method that solves them both, and many more. So the takeaway, the knapsack asks you to pick items for maximum value within a weight limit, and the longest common subsequence asks for the longest ordered pattern shared by two sequences and 80-1-2 two very different looking problems that, as we will see, are solved by the very same dynamic programming method of filling a table. So learning one teaches you both. Let us set up the knapsack problem concretely, because a clear setup is half the solution. You have a bag with a fixed weight capacity and A212, say 10 kilograms. The capacity is the hard constraint. Whatever you choose, the total weight cannot exceed it. This limit is what makes the problem interesting. Without it, you would simply take everything. And you have a set of items, each described by two numbers, its weight and its value. One item might weigh 6 kilograms and be worth 30. Another might weigh 3 kilograms and be worth 14. Another 4 kilograms worth 16. The weights tell you how much of your precious capacity each item consumes, and the values tell you how much you gain by taking it. The tension is obvious. Heavy items might be valuable, but they eat your capacity, crowding out other items you could have taken. The goal is to choose a subset of these items and 800 secti, some to take, the rest to leave, and 800 secti so that their combined weight fits within the capacity and their combined value is as large as possible. This is called the 0-1 knapsack because for each item, you make a binary 0 or 1 decision. Either you take the whole item or you leave it entirely empty 1T1T1. You cannot take half an item. Mnemonic binary choice, made for every item under a shared capacity constraint, is the whole problem. It sounds simple, but the number of possible subsets is exponential. So checking them all is hopeless for many items anti-AT12, which is exactly why we need dynamic programming. The setup is a capacity, a list of weighted and valued items, and the aim of the most valuable subset that fits. Hold that picture. The solution grows directly from it. So the takeaway, the 0-1 knapsack gives you a bag with a fixed weight capacity and items each having a weight and a value, and asks for the subset that fits within the capacity while maximizing total value, and AT202 with a binary take it or leave it choice per item. The exponential number of subsets is why we solve it with dynamic programming rather than brute force. Now let us find the heart of the knapsack solution, the recurrence, which comes from a single simple question asked about each item. Consider any one item and think about the two things you can do with it and A2112, the binary choice. This gives two scenarios to compare, and the best answer is whichever of the two is better. Framing every item as this either-or decision is what turns the whole problem into a recurrence. The first choice, leave the item. If you do not take this item, then the best value you can achieve is simply the best value achievable using only the remaining items. With your full weight capacity still intact and 82 to fall, you spent none of it on this item. So ain A2 ponis, leave it, and A2 ponis 2 ponis reduces to the same knapsack problem on the other items with the same budget. It is a smaller version of the very same problem. The second choice, take the item N8012, but only if it fits. If you take it, you gain its value immediately, but you use up some of your capacity equal to its weight. So the total is this item and a CN9S value, plus the best value achievable from the remaining items with a reduced budget and 812, the capacity minus this item and a weight. Again, that N A2 at1, best from the remaining items and A1 or 1 is a smaller knapsack subproblem. Now you simply compare the two results and A200 fall, the value from leaving it versus the value from taking it, and A200 fall and keep the larger. That comparison, take the better of leave it or take it, is the recurrence for the knapsack, and every subproblem is a smaller knapsack, so they overlap and we memoize them into a table. From this one, repeated question, applied down through all the items and capacities, the whole optimal answer is built. So the takeaway, the knapsack recurrence comes from one question per item and 8200 all. Leaving it gives the best value from the remaining items with the full budget, while taking it, if it fits, gives its value plus the best from the remaining items with the budget reduced by its weight, and 8 high 200, 200 and you keep the larger of the two, a recurrence over smaller knapsack subproblems that DP fills into a table. Now let us switch to the second problem, the longest common subsequence, and set it up just as carefully. First, we must be precise about what a subsequence is, because the definition is the whole subtlety. You are given two sequences and A212. Let us use two strings of letters. A subsequence is what you get by deleting some elements, possibly none, from a sequence while keeping the remaining ones in their original order. The keyword is order. The elements must stay in the same relative order they had, but they need not be adjacent, and A200 to Hove, you can skip over elements between them. So from AC out 200, 200, A BCBD A200 200. The letters BCB in that order form a subsequence, even though they are scattered through the string with other letters in between. That is different from a substring, which must be a contiguous chunk. A subsequence can have gaps. The longest common subsequence is then the longest subsequence that both of your sequences share. You are looking for the longest ordered pattern of elements that appears in both strings, each element in the same order in each gaps allowed. For our two example strings, the longest such shared pattern might be 4 letters long. Finding it means finding the deepest ordered commonality between the two sequences in A212. The longest thread of matching elements you can trace through both while only ever moving forward. This is a genuinely useful measure, which is why LCS appears so widely. It quantifies how similar two sequences are as ordered data. A long common subsequence means they share a lot of structure. A short one means they diverge. It is the idea behind tools that compare two versions of a document and highlight what stayed the same, behind comparisons of genetic sequences, and behind many similarity measures. And crucially for us, like the Knapsack, it has overlapping subproblems and an optimal substructure recurrence. So it too yields to dynamic programming and A202, which we find next by asking, once again, a simple question at the ends of the sequences. So the takeaway, a subsequence keeps elements in their original order but allows gaps between them, unlike a contiguous substring and A212, and the longest common subsequence is the longest such order pattern shared by two sequences, a widely used measure of their similarity that, like the Knapsack, has the overlapping subproblems and optimal substructure that make it a dynamic programming problem. Let us find the LCS recurrence, and you will see it comes from a simple question at the ends of the two sequences and 8512, beautifully parallel to the Knapsack and 3999 TT. Look at the last element of each of the two sequences and compare them. There are just two cases, and in each case, the answer reduces to the LCS of shorter sequences and A202 how smaller subproblems of the very same kind. Everything follows from which of the two cases you are in. Case 1. The two end elements match and AT212. They are the same. Then, that shared element can be the end of the common subsequence, so it contributes 1 to the length, and the rest of the answer is the longest common subsequence of the two sequences with those matching ends removed. In short, a match gives you 1 plus the LCS of what remains. Every time the ends agree, you have found one more element of the shared pattern and you shrink both sequences by 1. Case 2. The two end elements differ. Then, they cannot both be the end of a common subsequence, so at least one of them is not part of the answer, A212, but you do not know which. So you try both, compute the LCS if you drop the last element of the first sequence, compute the LCS if you drop the last element of the second, and take the larger of the two. A mismatch, then, means an A220, discard one end or the other, whichever leads to a longer result. An A221, between the two cases, an A220-12, match adds 1 and shrinks both. Mismatch drops an end and takes the better. An A220-12, you have the full recurrence. And every branch is a smaller LCS subproblem. They overlap heavily, so we store them in a table, exactly as with the Knapsack. Notice the parallel. Knapsack asked take or leave for each item. LCS asks match or skip at each end. Two problems, the same shape of decision. So the takeaway, the LCS recurrence, comes from comparing the last elements of the two sequences and A212. If they match, the answer is 1 plus the LCS of the rest. If they differ, it is the larger of the LCS after dropping one end or the other and A212. A two-case recurrence over smaller LCS subproblems, mirroring the Knapsack in 39's take or leave with its own match or skip. Now for the payoff. The reason we studied these two together, they are, underneath, the exact same technique. Let us make that shared pattern explicit. In both problems, the natural way to organize the subproblems is a two-dimensional table and A200 A200. A grid. For the Knapsack, one axis, is which items you are considering, and the other is how much capacity remains. Each cell holds the best value for that combination. For LCS, one axis is a position in the first sequence and the other a position in the second. Each cell holds the LCS length for those prefixes. In both cases, a cell of the table represents the answer to one specific subproblem, and the whole grid is the collection of all subproblems laid out neatly. And in both, you fill that grid cell by cell, bottom up using the recurrence and a total, each cell computed from a few already filled neighboring cells. The knapsack cell looks at the take and leave results, which sit in earlier cells. The LCS cell looks at the match or the two skip results, which sit in adjacent cells. You start from the simple base cases at the edges of the grid and work inward. And because every cell only depends on cells already computed, the whole table fills in cleanly. Each subproblem solved exactly once. This is tabulation from last class applied to a two-dimensional table. Finally, the answer to the whole problem sits in one particular cell and 8212, typically the last one, the corner representing the full problem with all items and all capacity, or both complete sequences. You fill the grid, and then you simply read off that final cell. That is the shared pattern in full. Define what a cell means, write the recurrence that builds a cell from its neighbors, fill the grid from the base cases, and read the answer from the last cell. Knapsack and LCS differ only in what a cell means and what the recurrence says, and 8, 10, 12 above. The machinery around them is identical. Master this grid filling pattern, and you have not learned two problems. You have learned a whole method, and countless problems are just new fillings of the same grid. So the takeaway, both problems become a two-dimensional table, and A2112, a cell per subproblem, one axis for each item set or sequence, and A2112, that you fill cell by cell from the base cases using the recurrence. With each cell built from already computed neighbors, and the final answer read from the last cell. Knapsack and LCS differ only in a cell in 99. Meaning and recurrence, sharing one identical grid filling method. Let us turn that shared pattern into a concrete recipe you can apply to either problem or to a new one you have never seen. Step 1. Define the cell. State precisely, in words, what one entry of your table represents. For the knapsack and A2 sound, the best value using the first I items with capacity W, and A2 sound, the length of the longest common subsequence of the first I characters of one string and the first J of the other, and A2 sound, egg. This definition is the most important step and, as always in DP, the hardest, and 8 hours up house. Get the meaning of a cell right, and everything else follows almost mechanically. A fuzzy cell definition is the root of nearly every DP mistake. Step 2. Write the recurrence N A212, how to compute a cell from its neighbors N A212, and the base cases. For the knapsack, it is take or leave. The cell is the larger of leaving the item, the cell above, or taking it, its value plus an earlier cell. For LCS, it is match or skip. If the characters match, 1 plus the diagonal cell. If not, the larger of the cell above or the cell to the left. And the base cases are the easy edges. 0 items or 0 length sequences give 0. With the cell defined, these recurrences read almost directly off the take or leave and match or skip logic we found. Step 3. Fill the grid and read the answer. Loop over the table filling each cell from its neighbors, starting at the base case edges and working to the far corner. Then read the final cell and 8212. That corner is the answer to the whole problem. That is the entire method, and it is the same for both problems. Define the cell, write the recurrence and base cases, fill the grid, read the corner. Once this recipe is second nature, a huge range of optimization and sequence problems become approachable, because you stop asking an A2200 what clever trick solves this, and A2200 and start asking an A2200 what is a cell, and what is the recurrence, and A200. That shift in questioning is the real gift of studying these classics. So the takeaway, apply one recipe to both and A21. Define precisely what a table cell means, the crucial, hardest step. Write the recurrence that builds a cell from its neighbors, plus the base cases. Then fill the grid from the edges to the corner and read the answer there. Knapsack and LCS followed this identical method, and so do a huge range of other problems. Before we recap, let us build the instinct that matters most in practice, recognizing when a new problem is one of these classics in disguise. When you see a problem that says, in effect, NA2200, choose a subset of things to maximize some value under a limit or budget, NA200-200, your knapsack alarm should ring. Selecting projects under a budget, packing under a weight or size cap, choosing items to hit a target, and 8 whole, these are knapsack shaped, with a take or leave decision per item and a capacity constraint. The moment you spot an A2020, pick some, not all, best total, within a limit and A21, reach for the knapsack template. And when you see a problem about the longest shared or common ordered pattern between two sequences and A200 half, or a similarity or edit distance between two strings and A200 half, think as CS style grid. Comparing two versions to find what is shared, aligning two sequences, measuring how alike two ordered things are. These have the match or skip flavor, and fill a two-dimensional table indexed by positions in each sequence. Whenever two sequences are being compared for shared structure, an LCS like DP is often the key. And above all, whichever it is, start by defining the cell. The single most useful habit in dynamic programming is to force yourself to state in one clear sentence what one entry of your table means before you write any code. Nail that, and the recurrence tends to reveal itself because it is just an A200-200. How do I build this cell from smaller cells of the same meaning, A200-1D1? Recognize the knapsack and LCS shapes. And define your cell crisply and A12 those two habits turn these classics from things you memorize into a lens you apply. A great many interview and real-world problems are, at heart, a knapsack or an LCS in a costume. And now you can see through the costume. So the takeaway, build the recognition instinct and A2525 and A25. Choose a subset for the best value under a limit A255, signals a knapsack, and A255, longest shared or common ordered pattern between two sequences and A2555, signals an LCS style grid, and A255, K2555. Always start by defining the table cell in one clear sentence, from which the recurrence follows. Many problems are these classics in disguise. Let us gather the whole class in one breath. Two famous problems, an A212, the knapsack, and the longest common subsequence, an A212, share one dynamic programming method. The knapsack, choose items for maximum value within a weight limit. Its recurrence is take or leave, and 8 ho or I212 for each item, keep the better of taking it or leaving it. LCS, the longest ordered pattern shared by two sequences, gaps allowed. Its recurrence is match or skip and A202. A match adds 1, a mismatch drops an end and takes the better. And both are the same pattern. Fill a grid cell by cell from the base cases and read the answer from the final cell. Next class, an A21, QoFs, modeling connections and relationships. One idea at a time. That is classic dynamic